from, as you can see, from Eindhoven and from the chats, and we'll talk about DevOps continuous architecting with TOSCA. So we are back to TOSCA again.
Yes, definitely. Well, only this time, not as many pictures as the last time, Frank. He had his fill of pictures. Okay, so thanks for the intro. I will do a bit of an intro myself, as a matter of fact. My name is Damian, and I prepared this talk. It's supposed to be a tutorial we're going to share in the next hour, but it's very informal, so if you have questions or issues or doubts, just raise your hand.
Can you also say something about JAWS itself?
Sure,
yeah?
Sure. The Hieronymus Academy of Data Science is called Hieronymus after Hieronymus Bosch, because it's built in Den Bosch, or 's-Hertogenbosch, or Herzogsbosch, for those Germans you out there.
Nothing to do with the company Bosch.
It has nothing to do with drills either, nothing to do like that. Actually, it's a joint initiative between TUE. I'm going to turn this into a publicity stunt. It's a joint initiative between the Technical University of Eindhoven and Tilburg University. So I am from Eindhoven and Willem-Jan is from Tilburg, as a matter of fact, and we are leading the JADE Lab, Data and Engineering. So we, for example, apply data science in the context of big data and software engineering and distributed systems engineering, microservices, and things like that. But the Academy's mission is to address societal and large-scale industrial problems with data science. So anything that comes to mind which falls into that domain, which is arguably very big, fits into our mission. So if you have any ideas, just come ring our door. We are hiring big time. We need talent, even full professors. So if any of you are looking for a long extended sabbatical, you want to write a book, we also invited Marco, but Marco chose to go in Australia.
He will send you his application tomorrow.
Sure, we will consider it carefully, Volker. And we will give you, maybe, if you're good enough, we will give you the software design course. How's that?
You see, I was so often in Holland, I would not recommend to do that.
Come on. Anyway.
Oh, it's raining, right?
No. It's not as raining. You might think that it's raining, but it's not. It's actually close to Germany, and the Germany kind, which is dear to my heart. As I will tell you, I also worked in Darmstadt for 2 years for the European Space Agency, and that was a beautiful time. Very good weather.
But it's always windy.
Yeah, it's
So come on, let's continue.
Anyway, sorry. However, I did choose to start from some basics about this guy, Damian. Who is this guy? Why is he not taking some sun outside? So I was born from a scientific perspective at the University of L'Aquila in Italy, a small town, but a very big name in software architectures and formal methods for software architectures. So I was born in that way. I was a formalist. But then my bachelor's degree became a proposal for the European Space Agency, or a project, or a call for proposals that they had about architecture requiring round-trip engineering, abstract concepts that nobody knew anything about. So I went to the European Space Agency. The mission was successful. There was a lot of hair ago, I have to admit. So we completed that after a couple of years, and then I went back to university because I didn't want to just stay a formalist. I love formal methods as much as the next guy, but I want to be practical. I want to help the industrial people. I want to help the practitioners that I'm working for. So I went back to University of L'Aquila. I got yet another formal master's degree, as it turns out, on formal methods for representation and reasoning. And then I got into global software engineering, which is arguably much more practical. And then after that, I did my PhD as well at the University of Amsterdam. By the way, my affiliation is wrong. That's what we were saying this morning. Because I was at the University of Amsterdam only for my PhD. That's how I came to SummerSOC for the first time. It's Frank's fault. But yes. So anything I do, it's his fault. We'll talk to him. Anyway, I finished my PhD 1 year in advance because I wanted to write a European project, which I did and won. So the project was about software architectures in big data, as it turns out. Because everybody was involved in big data, and I wanted a share of the pie. So that project was completed, and then I went back to the Anonymous Academy of Data Science, because big data, and it's fun. And I want to share the fun. Okay, so what am I doing there, and why is this talk something that might interest you guys and girls? Well, I will try to introduce it to you as far as I have understood it. Mind you, none of this came from academia. All of it came from practitioners. So if you have any question, I can answer from the academic perspective. I hope to answer also to what extent that they would answer. Anyway, I'm going to tell you what it is, where it comes from, what it is about, how does TOSCA fit in, how you can actually take care of it, and some conclusions, take-home messages, maybe something you can do the rest of your research career. But first of all, continuous architecting. I know those faces. I've seen those faces plenty of times. I gave this talk to Wien, and you have no idea those are Viennese people, what faces they give. So, has anybody heard of continuous architecting yet? Ever?
Continuous engineering.
Awesome. Awesome. Yeah, probably continuous or DevOps engineers. So where does it come from? Well, if you Google it, you will find that there's a large number of practitioners that have written articles about what continuous architecting actually is. But I can tell you they don't agree, as it turns out. None of them have a clear idea about what it is. And also, academics are not even looking into it yet. Some of them are, like myself, but this is work from last year. So the first thing I did, as the skeptical mind that it's in my brain, obviously I was pretty much amazed, and I had really this face. Right? So I started wondering, and I wanted to give it some sort of formal sense. That's how I was born. So I took a step back, and I said to myself, what are they usually considered to be? So the software architecture public would agree that software architecture is a series of design decisions. And that's usually the common knowledge around software architectures today. So by opposite, or by comparison, continuous architecting means that if you have a series of software architecture decisions, which are sort of detached, they're made by a human, they're carefully evaluated. Continuous architecting, as opposed to that, is a continuous series of decisions. It's a series of decisions where you cannot distinguish who is making the decision, where is the decision actually taking place, whether it's a machine taking the decision, what is the rationale for those decisions. So the decisions are really emergent. They are a continuous artifact. There is no distinction between two separate decisions. They can actually coexist at the same timestamp from a more formal perspective. So again, software architecture is a set of design decisions. That definition was from Jan Bosch. As a matter of fact, you can find it in literature. It's not something I invented.
Sorry, it should not be
Yes.
a set of design decisions, a sequence of design decisions.
Yes.
Because there's an order.
Sorry. Yeah, correct. Sorry, my mistake. Typo. Actually, I'm going to type that down.
I'm not a formalist, but sometimes it gets me.
Yeah, that's true.
Usually, Wolfgang is the one who figures that out.
Wolfgang, you should have catched that.
You're right, I'm sorry to have.
Anyway, documented series or sequence of design decisions. Yes, thanks. By way of comparison, what you have on the other side is, again, there you go. Oh, sorry. There you go. So you have decisions that are emerging in an automated fashion. You can think of this as connected to liquid computing, for example, or any number of areas that you yourselves have shaped, as a matter of fact. Self-adaptive systems do fall into this category, I would say. Because decision-making from a human is only made when extremely needed.
What does that mean?
I'm sorry?
What does extremely mean?
The book doesn't say. That's actually a very good question. We will get to that. We will get to that. Because extremely, there's some formalism missing behind, I think. So you make everything as a product, you leverage the small, but when you want to change the small, I presume that's an extreme condition. So for example, you want to change the internals of the small, or how the small relates to the large, and so on. But this is not clear to any stretch of the
I don't understand what you mean with make everything as a product.
So the services themselves are componentized,
Yeah.
as Wolfgang was illustrating a few days ago, but also a few years ago, arguably. And you sell that component, so it's microservice.
But what does it mean in the context of architecting?
Well, essentially you use microservices to build your own architecture.
Oh,
Because
I
you
see.
can sell each individual microservice as its own unit, and you make every piece of the equation something that you can sell. Does that make sense?
Reasonably. I listen. I listen.
Right. Okay. It doesn't make sense to me either. That's why I have this slide here. Because still, again, there's a lot of work to be done, I think. And also the practitioners themselves don't really agree in this. So this is your face.
Yes.
But this is my face.
No.
What I more or less. What I did when I actually looked into this, and none of this was clear to me. So I took a step back, when it actually began. I took a bit of a history walkthrough. Now the origin of the concept, as a matter of fact, was around 2013. Now for those of you who are big fans of DevOps, such as I am, you would know that 2013 was a very important year. The Trump disaster hadn't happened yet. The Italy election had not happened yet, so a lot of disasters didn't happen yet, so it was a happy time in the world. But it was not really a happy time in the software world, because as it turns out, the top 10 causes of software failure were pretty much the same until 15 years previously. And this is extracted from the Gartner report of 2013, so that year, the software failure, the top software failure causes are not changed. They're still the same. So regardless of what the software engineering community is doing, it's not working. Right?
I already say this looks like 40 years ago.
Yes, yes. I went back 15 years.
Oh, I see.
Just to make sure.
Oh, I see.
I was not there 40 years ago. Anyway, so just to give you an example of these causes, which is fairly recent and relating to that year, and Ramesh would have liked this example, witnessed one of the biggest disasters in software history of the United States. It happens to relate to e-health, but it's just one of them. There's plenty. You can find another one in the Dreamliner. Dreamliner is this big, huge, and fancy plane which was landed beforehand because the brakes officer was not working.
Similar things happened to the Airbus a couple of years before.
Yeah, for example. And there's plenty. So in response to this, DevOps, as Len would put it, Len Bass actually had one of the first books on DevOps. So Len says DevOps is a series of practices to try to address these problems. You have several sorts of practices. You have practices that relate to acceleration. So you want to make your process more speedy. You want to use tools, automations to actually build, integrate, test, deploy your software continuously as fast as possible, such that if your software really wants to fail, because it wants to, then you'll figure it out faster. So that's the principle. You want also waste reduction. You want to do waste reduction because you want to make sure that whatever resources you are spending actually amount to as much as possible in terms of return. But also, as it turns out, and this is extracted from Len's book, so it's a pretty interesting area, you have omniscience tactics. And I'm going to deal into that in a second. So, acceleration tactics, a few examples, they're extracted from the book. Again, it's not something that I invented. In terms of acceleration, you have infrastructure as code, which is TOSCA. You have continuous integration, continuous deployment, which is TOSCA, by the way. Continuous testing, in terms of waste reduction, you have canary testing, sandbox testing, all of these sorts of practices that practitioners are actually using. Minimalistic architecting, like microservices, this is what we were saying. Product-based, minimalistic. What about omniscience? Omniscience means I want to know everything. It's loosely based from the Oxford Dictionary. I want to know everything about my product, of course, and my people. Not only the product, also the process, the people who are involved in the product. I want to monitor everything, not only the product, also the people, everything. The organizational structure, who collaborates with whom, who is working on what, where, when, why, and so on and so forth. We can actually build, or rather, practitioners have proposed monitoring as a service. So monitoring factories that build analytics which are specific to certain product types, like DataOps. On-the-fly risk engineering. And among these omniscience tactics, as it turns out, Murat, from the book that I showed you earlier, places continuous architecting. What does it mean? What is this beast that he calls continuous architecting? This is how I see it, as a synthesis of his book. He says, software architecture responds to architecture drivers. So the reason why you're making those decisions is because you have drivers, either for products, for markets, for people, whatever. In terms of continuous architecting, you want to upgrade those drivers to make the architecture consistent with use in DevOps. So you are designing the architecture for modifiability, which is something that also a few of you have looked into. You want to design for observability. You want to design the architecture in such a way that you can monitor it from every angle, from every perspective. For organizability, you want to design your architecture in such a way that every microservice is allocated to a single person, for example. Netflix does this. Netflix has adopted a DevOps model, which is called NoOps, because a single developer is associated with his own, her own microservice. That's how they actually produce. Because that is designing for high scalability and how integrability. But among these, you're designing for failure. Because DevOps means you want to fail as fast as possible. Success is no longer your driver. Failure is your driver. You want to rig the architecture in such a way that you can actually force it to fail as soon as possible, with test cases, with a huge client load, with whatever. And you want to do that continuously. Because the only way in which you will achieve a stable or a ROI-giving architecture, return on investment giving architecture, is by making that architecture fail, maybe in safe conditions, like in a sandbox, as many times as possible, as you can, and as fast as possible, in such a way that you can improve it. By seeing how it works, seeing how the people relate to it, and learn also. And this is actually a machine. No question?
Really, design for failure is not more like design with worst case testing all around.
Could be, yeah, sure. I mean, this is a tactic, which means you can implement, how you implement it is your business. Yeah, but yes, in principle, that's yes.
I'm a simple-minded guy. I only know databases. So I'm trying to generalize from what I learned there. Very often there is no one solution or one architecture, but there might be alternatives, and one is not a failure, the other one is not a failure, but one might be, according to a metric, better than the other one.
Yeah.
So how do you deal with that?
It's a very good point. I can tell you how I would deal with that. Or using these principles. So essentially using these principles, you would implement both in different microservices, such that you can present them to
100 years here, 100 years here.
Yeah, I agree. It could be a waste. Yeah. That's actually one of the problems I have with this. And as a matter of fact, one of the products that I helped build could maybe limit the problem, but it's a matter of trade-off still. So it's still the same in a different flavor. And that's my conclusion. But spoilers, it's the conclusion. Okay, so what does this mean from a practical sense? Here you have the usual DevOps bicycle, which as a matter of fact is a spin-off of our S-Cube bicycle. So we invented this before DevOps was a thing. So your dev goal is to prepare a software architecture which is shitty because it's designed to fail. You want to deploy that architecture as fast as possible because you want to improve it continuously. That's it. So you take this bicycle, you put together a number of tools that do that automatically for you. Continuous architecting is how you build the architecture in a shitty way, in such a way, however, that it can be deployed immediately and as soon as possible, and as fast as possible. But also you rig it with continuous integration techniques, continuous deployment techniques, continuous testing techniques. All of this needs to happen at the same time, possibly in an automated fashion as much as possible. Now, let's reason on the bicycle for a second. These are standard terminologies. This, again, is not something I invented. well, actually Frank and a bunch of other big top pros invented in the scope of SQ. So, however, out of this bicycle, you have the delivery loop. Delivery is where TOSCA comes alive. So, how does that architecture, which is supposed to be shitty and is supposed to be delivered as fast as possible, how does that relate with provisioning for that architecture? How does that relate with building an infrastructure which is contiguous to its quote-unquote shittiness? And how do you actually monitor it for it? Well, spoiler alert, as it turns out, that's exactly where TOSCA comes in. So, this is where TOSCA lives. TOSCA is, well, as many of you know, I hope, but then I have a digest, so don't worry if you don't. As you know, TOSCA is a standard from Oasis, with which I have been playing around with for about 5 years now, pretty much. So TOSCA simply reflects the infrastructure and the application together. It is a blueprint of the artifacts, or what is called the application deployment topology. Topology is a graph of artifacts, like the one that you're seeing here. It's a graph of physical artifacts, it's a graph of nodes, it's a graph of strongly typed nodes and edges. And you need to specify procurement, installation, configuration, deployment, everything that graph needs to exist in the cloud. It's supposed to be in the blueprint, right? So TOSCA is actually a standard for that. So how do you make the architecture consistent with being deployed as fast as possible using that artifact? That's the answer that we are trying to look for. Okay, so this is a digest about TOSCA. How many of you have not heard about TOSCA? Have not heard? Because I can skip this. You can get to the most interesting part. Not heard? So you all know about TOSCA? Awesome. Let me skip this. It'll be fun. Skip that. Actually, I added it because Marco wanted to see it, so it's his fault. I'm going to focus, however, on the least understood part of TOSCA. Policies, which not many practitioners dare to enter. As a matter of fact, not many researchers dare to either. As far as I've seen, maybe some of you have different opinions. Now, what are policies? Policies are areas of the blueprint that dictate, sorry, there you go. Area of the blueprint that dictate, where is it? Okay, confused?
No, we are done, thank you.
I had an example of the structure of the blueprint. Yeah, anyway. Policies are what tell the orchestrator how to behave with respect to the blueprint. That's it. So they constrain the behavior that the orchestrator is supposed to exhibit given a certain triple, an event, a series of conditions, one or more, and an action that the orchestrator is supposed to undertake. An action. And these are up to you. As far as you define the types and you make it consistent, you can actually have the orchestrator dance ballerina if you want. Several types of policies which are standard have already been defined. So quality of service, like for example, elasticity policies, placement. You don't want your nodes to be stored in Arabia or something. And here's an example. This is extracted directly from the spec. I actually quoted some of that as well myself. You have an event type. Based on the event type, the policy says, orchestrator, please do this and that for me, if this condition emerges. That's it. It's reasonably simple. So, just putting it all together, you have your TOSCA blueprint over here. You have your workflows, your PMN, you have your policies, your nodes, your edges. I also have a couple of examples that I can skip. So, how does continuous architecting relate to it? Where does it fit in? Why does it make sense, if it makes sense? Well, I try to elicit these two ways from the books, but many of them, to be honest, they don't really relate to what I think. As a matter of fact, some of the concepts herein need desperate attempts at research. So the simple way is you use policies for automated architecture decision making. This can mean that your orchestrator can change your architecture. It means that, well, first of all, it assumes that your architecture can be changed by the orchestrator.
Based on what? Based on what you want to make this change in automated?
Yeah, policies. Event condition actions. So for example, I have my microservice and I encounter a workload which is dense with clients that have certain behavior, which means I want to rearrange my architecture to actually cope with that. But the orchestrator can do it for you. You don't need a human to do it. So you use policies in a TOSCA document using TOSCA operational semantics to actually change the structure of the architecture. Structure and properties, because mind you, architecture by definition is structure, visible properties, and quality of service. You continuously evaluate those decisions against whatever SLAs are behind those policies. This also means using monitoring, using trace checking, for example. That's what we did at Politecnico di Milano. But also, you need to instrument a DevOps pipeline to measure all sorts of quantities, which means the orchestrator is no longer just an executor, it's an intelligent machine, because it needs to understand what is happening in the context, what is happening for the application, but also of the clients and of the people working with that product, and so on and so forth. Because you need to rig the orchestrator to help you with respect to continuous improvement. And this, my friends, is supposed to be a simple way. More or less simple. Although this, I think, is true in principle, is not necessarily true in practice. How do you do it the hard way? And this is pretty much extracted from Erdder and Murat's book. You use TOSCA Blueprint to actually model everything. To model the DevOps pipeline, to model the organizational structure which is working with that DevOps pipeline team, the software architecture which is maintained, so the series of microservices which are included, all in one single giant unmaintainable blueprint. And obviously you use TOSCA-based orchestration, so you fiddle around with the orchestrator, you deploy monitoring techniques, you deploy runtime model checking techniques such that you can actually make sure that the orchestrator works continuously to improve whatever that blueprint says. And this to me is just phantom menace. However, there is some work that I did to make it as real as possible. This is the example that I want to show you, because some of it can actually be made real, but only to a certain extent, and I will discuss the limitations of what I'm about to say at the end of this, but again, feel free to throw a picture at me if you want to ask a question. So we try to apply this concept, so continuous architecting, to big data applications. Now for those of you who are familiar with big data applications, you must know that, as a matter of fact, big data application is just a middleware that runs a certain topology itself. It can be actually seen as an SQL statement that looks for results in a large chunk of data. You have middleware, you want to run something using that middleware. However, a large piece of making that middleware work is its own configuration, how it relates to the infrastructure, what is its structure, so if it relates to other pieces of middleware, such as other databases and so on. So the architectural challenges are pretty clear. And we wanted to build a DevOps pipeline for that. And we wanted to support this sort of continuous architecting of these big data applications. Using model-driven engineering was actually my first go-to. And this is the project DICE that I'm talking to about here. The project is concluded, so if you want to get a concrete look into whatever I'm about to say, you can actually browse the website, it's up there. So you use model-driven engineering to try and support some of the statements that we have illustrated up to this point. How we actually did that, this you might recognize it as a common stack for model-driven engineering, so you have a very abstract representation of your big data application, a platform-independent model, and then you have a technology-specific model. So for example, in the platform-independent model, you have compute nodes. In specific model, you have Apache Storm nodes, Apache Spark nodes, or whatever middleware you can think of. In the deployment specific model, you have the infrastructure, which is related to those nodes. So you have pure architecture, let's say design, so a series of design decisions, instantiation of technology. And then you have deployment architecture. And there's automated back and forth transformation between these layers.
Damian, your vision basically is only modified the TOSCA blueprint, right?
Yes.
So you lose all the important
Aha!
information. This is all I wanted to say. It seems to be misuse of TOSCA.
Yes, I think so. Yes.
Okay, good.
I think it's also a dangerous override of TOSCA.
Yeah, absolutely.
If you don't program, that's what we found at the end of the project. If you don't program the blueprint right, it's going to cause more problems than it solves. And I'm about to show you what problems we had. So the first problem was so Dicer is live, and the tool is there. You can actually use it. But this is actually a tutorial on what not to do in this context, I would say. So the tool is there. It actually has its own delivery service. You can actually use it. It features TOSCA, obviously. What it does is assume a series of platform parameters that you can also tune with analysis, so you can do your design. But here comes the first problem. If you tune your design and you build your blueprint, you lose the ability to go back. So you need to wait until the DevOps loop is finished. So you need to wait until your application is deployed. Monitoring actually comes in, and you get feedback from the monitoring. That's the only way in which you can change your design. So you need to stop doing the architectural and classical design that you were doing before and start thinking about improving the architecture itself. So you have containers, you have deployment, you have platform parameters that change as a consequence of the deployment structure. Obviously you need a library, and the library is what is defined as a series of components that you are deploying. And this is also yet another limitation. As it turns out, if you want to do it this fast, or rather, if you want to do it at all, you need a library which self-updates. Can you guess the frequency at which big data technology evolves? How many revisions on average per day do you think a big data application or middleware is redeployed by the maintainers? Take a guess. Come on, you have 1 minute.
20 times.
Something like that, 10 times on average. Depending on the middleware, depending on how the community is active, which also means that whatever node you have here is bogus after an hour. You need to update it. Now, in our library, we had about 40-ish nodes, more or less.
Can I become a little bit more concrete? So at time I, you say I use Hadoop to solve a certain big data problem.
Yes.
And then at time I+1, you say, Hadoop is too slow. I use Spark, and I run through this process, and out comes rather than a Hadoop job, it comes out a Spark job that
Yes.
gets deployed and everything.
That was the point initially for us. It was
It sounds like dreams.
the dreams, you mean?
I mean, is that real? Is that realistic?
So it is real with the assumptions that we made it real, right? So you can do this sort of trade-off analysis at design. The problem is, once you have done that, once you have chosen, you cannot go back. So whatever effort you have
I would
invested.
be happy only if I could somehow generate automatically things for the different platforms.
Yes, that you can do. That you can do. That is already real. That you can do already with the tool. It's fun. I promise.
I've never heard of that. I mean, some people look for that.
Yes, we are actually selling this. If you're interested in
Sound
buying
more to me like a magician.
Yeah, but we were pretty good. We got an excellent from the European Union, which means we must have done something right. But again, even if it does work, it's not perfect. Also because, again, the architectural assumptions that you're making, the nodes that we selected, are rigged with those decisions. We made the decisions for you. You cannot choose a different version of Spark. You cannot choose a different version of Storm unless you go and change it yourself. What we can do for you is build the infrastructure, because that mostly stays the same. Mostly. But again, it is real to some respect, but it makes so many assumptions, and those assumptions become architectural decisions that are rigged by design in whatever automation. This is a problem which is common in automation. If you go and ask Dave Parnas, he will tell you the same thing. He was telling about this 20, 30 years ago. So whatever decisions we made, whatever architectural decisions we made for these nodes are still there. So it's not like nobody is making decisions. Somebody else has made them already. That's the point. But anyway, there's fun in that, in the sense that because of TOSCA, you can actually change the infrastructure there, and the infrastructure stays real, which means that the tool will still be able to build up whatever infrastructure and deployment requirements your data-intensive application actually has, so that's good. But also another number of tools you can use. So this is Dicer, the tool that I'm talking about. This generates the 3 layers, but it also allows for simulation, optimization, and verification of your design, because we figured out that if you cannot go back, you need to make sure that you really want to go forward. And so you need really to be finished with your design before you move forward. So you want to simulate your topology, you want to simulate your data-intensive architecture, you want to optimize it for the right infrastructure. And when you are sure, and this is, mind you, this is building the first version of the software architecture. When you are sure, you build your infrastructure and you start continuously improving it. Now here comes another problem. When are you sure? What is the stopping condition of that initial software architecting? We actually asked practitioners, and nobody knew. This answer is still unanswered. As a matter of fact, we did several trials with the tool and compared this time, this chronometric assessment, the way it is called, to the actual time that is required by a software architect in reality to build his or her own solution. And the 2 times, let's face it, they're really consistent with each other. Most of what you gain is there, is in the fact that you have your development side here and your operations side there, and the tool which is in between. So this generates and maintains consistent your infrastructure. Most of your gain is there. Most of your gain is still in infrastructure automation. It has nothing to do with architecting. It does to some respect in the sense that once you deploy, you can keep on improving. So that's where I would say the second major benefit comes in. Because once you deploy your application, once you are in ops, you can do configuration optimization. You can do fault injection. You can quality test with assertions using your TOSCA infrastructure. You monitor for stuff. And as a matter of fact, we have a tool that automatically feeds the monitoring into the model. So the model changes, but you have to redeploy it. The model does change automatically, but you have to redeploy it because it is your decision. And there is maybe some way to automate it. So something that we were working on request by the European Commission was, how about I take an agent which takes the numbers and decides whether or not that model can be deployed. So I take a machine learning model, I feed the data that I have, and I decide, using whatever modification I have done on the model, whether or not it is convenient for me to go forward with it, whether or not it is convenient for me to demarshal my already deployed application and remarshal a new one. We didn't manage. Spoilers. This is still pending. Just to leave good time for more questions, in conclusion, continuous architecting just means, at least from the literature, new architecture drivers. But as a matter of fact, as it turns out, many of them are not new. Modifiability analysis was defined by my advisor, a PhD advisor called a gentleman by the name of Hans van Vliet. He was working on modifiability analysis in the 80s, late 80s. Organizability, that's Conway's Law. So it's really nothing new. Conway's Law has been around for about 40 years. I myself have been involved in trying to prove it with several failed failed attempts at that. There's a few that are actually new. So what does it mean to design for failure? There's different interpretations of that. And there's no theory around that as well. So there should be theory. There's ample opportunity here. But also design for speed. I mean, microservices do help. Now we are going towards serverless computing, which means essentially your architecture is entirely contained in the blueprint. Because all of the functions that make up the behavior of your architecture are single functions that can actually be self-contained in an entire blueprint, in an infrastructure code snippet. So designing for speed is definitely new, but nobody really knows what it entails yet. And observability, this is something I have started looking into. So I want to try and formalize a number of metrics around observability. As a matter of fact, I wrote an ESOC paper for it that was just accepted this morning, so you might be interested in jumping by in September in ESOC. If you're there, just come find me. Okay, so only a few of them are actually new. Continuous architecting, key conclusion, is really more of the same. It's really more of the same. It's only faster. And the fact that TOSCA makes it faster doesn't make it easier, it actually makes it more complex. From an architectural perspective, I added this slide for Marco Aiello, who is not here. I will actually tell him off. From an architectural perspective, you definitely need to work on improving the connection between the infrastructure and the actual architecture. So creating a bit more seamless infrastructure and architecture link, that's definitely a big challenge. Also, comparison and trade-off analysis. Carrying out trade-off analysis is an established technique. Rick Hasman introduced it over 20 years ago. It has been gaining traction in industry. But how do you actually compare different software versions in terms of big data, for example? Several platforms or different releases of the same platform are completely different. So this needs to update as well. And also measure it. If you want to have omniscience, it means you need to measure stuff. You need to measure it rigorously, precisely. You need to know what to do with the measurements. It is no longer acceptable that you have a metric without knowing what to do with it from an improvement perspective. And lastly, and I was given this question by Rick Hasman himself, the man behind software architectures, who is the architect? So if we no longer have a person who takes the architectural decisions, who is actually the architect? And I started wondering about that myself. As a matter of fact, I don't have an answer. Maybe you have different answers that I can. I think, it's my opinion, so take it with a grain of salt. I think the architect is anybody who enables continuous start. So anybody who is working towards enabling the DevOps pipeline to work a little better is your architect, because it's speeding up the process of improvement of the architecture. Anyone who enables an agile organization, so even the manager in the company that chooses to adopt DevOps is an architect, because it will eventually improve it the way in which the product is going to be prepared. So the architect is really a community shepherd, is a person who cares for the social and organizational aspects of the software. The architect is my shepherd. It was a rephrasing of a very famous quote. And that's it. So I'm pasting in a few links of DICE, of the European project that I was mentioning. Just go crazy with it. It's done, so I'm no longer responsible for it. I was work package leader of DICER, so if you're interested in that, just come find me. That's it. Questions?
Okay, thank you. Are there more questions?
I still wonder between the point you mentioned, where do you start with the first architecture to go on with the continuous things? And as I understand it, the later things like how many instantiation on what machine and all these things, that's for me configuration, that's not architecture for me.
Yeah.
And so you do that continuous and you monitor and so that's okay for me, but I don't think once you decided for one architecture and you only have these small continuous steps, where I even wonder how to organize it if you have things that
Flash.
clash, yeah. Then you're stuck with your architecture and the rest is details, right?
Yes.
Yeah, I can add to it. I was wondering what your understanding of architecture is. For me, it was always on a conceptual level, clearly distinguishing from the implementation. You might have a component X, and you might implement it in 5 different ways.
Right.
So the implementation or the deployment or whatever you call it, is that architecture or is that something else?
Yeah, I think
And I think you have to be clear about it, because whether or not components should be separate or should be combined to something new is something else than saying, I want to implement this component by X, Y, or Z, and so on.
You have this nice slide with these 3 levels for the model-driven environment. Maybe you can explain it there, what's the level you really work on with your continuous integration.
I think it's this one, right?
Yeah.
Right, so in model-driven engineering, or its standard model-driven architecture, what you have is these 3 standard layers. This is really nothing new. So all 3 reflect architecture from 3 different views. This is state of the art. This is not something I invented. So these are 3 different viewpoints over the architecture itself. Anyway, that's how we.
I would not call it viewpoints. I would say refinements, because you go from something very
They're not necessarily refinements.
independent, as you say, to something that is very dependent on your particular environment.
They might also be refinements, but not necessarily. Because, for example, as you move from the platform-independent model, you are doing the refinements incrementally there as well.
Mm-hmm.
You're making decisions, you build the platform, the technology-specific model.
Right.
And then you go back, and then you add a new one, and you build another technology-specific one. And you compare them. This is exactly what you were saying just now. So there are different views of the potential implementation, so candidates, that's how we call them, right? But then...
So now, use this model and tell me what do you mean with continuous architectural changes? Is that on all 3 levels? On the lower ones, on the top one?
No, I think what we say is that it reflects how you change this artifact here. Because this artifact here contains all 3. Contains details of all 3.
So this is your knowledge base, the blueprint.
Pretty much, yes.
The accumulated knowledge about all the past, and you hope you can use it in the future.
Yes. Or you will use it in the future, and you will definitely change it.
This is a model I would not subscribe to. Again, my own experience from my database view, very limited. I think if we had followed that model, we would have had no chance to redesign things for, let's say, multi-core systems. Maybe you say, there are people who...
I can tell you one thing. It is very fast, but it's very difficult to change it. It's very difficult to change it unless by automated means. Because once you have this, once you have the models, the nice models well laid out, once you have those, you can monitor for the numbers to retune them, to change them automatically.
And your underlying assumption is that a software architect becomes superfluous.
I think that's a side effect.
No, that is a basic assumption here. And I believe there is some human value in there that you cannot replace.
I agree. Actually, there's a lot of knowledge that also goes lost. There's knowledge that is not captured or documented that also goes lost. So yes, I agree with you. Yeah. But that's a side effect of the project. We didn't design it in this way. We actually found that out eventually. Yes?
So my understanding of the model would be that to have the real overall model, the first model, and maybe some thinking and checking about the model will be the classical, the classical step from the software architect, and then adapting to changing environments, maybe changing to some extent to demands on the number of lines and all these things, which is for me not anymore real architecture. Is more like deployment on the deployment level. I can most of that
continuous architect.
You can tell it this way, but most of it will
change
will be on this level, mostly. And then I think that's really helpful to do that automatically because it has to be done fast.
I agree.
Less discipline doesn't mean you come up the next morning with an idea how to allocate some more virtual machines. That's too late.
Definitely. So what you would do in that instance is rerun the whole thing, because you're building another product. It's something new. it's yet another thing. It's not only the architecture you had before plus something else. That's why I said it's not necessarily an improvement of what you had before. It's something else new. It's on top of. Does that make sense?
Little bit. I would have used this model to talk about continuous 1, 2, 3 and say what are the specifics there? How do they impact each
yeah,
other?
it's something that we could do together, by all means. If you're interested.
I'm not an architect, I'm not a software person, I'm using only my simple mind.
I myself want to look into this because maybe there's value in it, maybe not. Maybe it means that.
And the
something
TOSCA
will
blueprint is
change.
still something magic to me, which I don't believe.
But it works. I can trust you. I can assure you. You would have done an awesome European Union reviewer at our last.
You are glad that you didn't have it?
No, I like challenges. You sound like a challenging.
So
Does that answer your question?
Are there more reviewers who want to ask questions? No? So thank you again. So let's go.